All right, let's just jump right in. If you've ever spent time prepping for a major software engineering role, you already know that managing memory under tight constraints is a massive favorite for hiring managers. So, in this explainer, we're going to unpack one of the absolute most notorious memory management puzzles out there.
Describe how you could use a single array to implement 3 stacks. You've probably seen this before, right? It's a direct prompt from the legendary Cracking the Coding interview book. And honestly, it sounds kind of simple at first glance. But between you and me, it's actually a brilliant, high-pressure test of how you handle edge cases, memory limits, and complex engineering trade-offs. We're going to break down 3 totally different ways to tackle this, going straight from a beginner's naive guess to a senior engineer's absolute masterpiece.
Now, I know we all know how a stack works, but just to make sure we're on the exact same page before writing any code, stacks operate on LIFO, last in, first out. Think of those spring-loaded plate dispensers at a cafeteria. The very last plate you push onto the top of the pile, that is absolutely the first one you're popping off when you need it. You can't just magically yank a plate from the bottom without moving everything else.
It's the classic LIFO versus FIFO showdown. While a queue is strictly first in, first out, like a literal ticket line where the oldest arrival gets served first, our stacks are only ever going to care about the newest item.
So to actually pass this interview challenge, our whiteboard code has to flawlessly support these 4 core mechanics across all 3 of our stacks. We need push, pop, peek, and is empty. But here's the absolute kicker. We have to pull off these additions and removals in constant time, meaning we cannot just shift massive blocks of data around every single time we make a tweak.
Okay, approach 1, fixed division. When most people hear 3 stacks, 1 array, this is almost always their first instinct.
It's super straightforward, right? You take your total array size, let's just call it n, and literally just chop it into thirds. You give each stack its own strict, immovable territory, and you just bump up a top pointer sequentially as you push data in.
Visually, this is incredibly clean. Stack 1 gets the first chunk starting at index 0, stack 2 gets the middle, and stack 3 gets the end. It's a breeze to code up because every stack is safely living inside its own little isolated memory bubble. They don't even know the other stacks exist.
But yeah, there's a fatal flaw here. What happens if stack 1 is getting hammered with a massive amount of data, but stacks 2 and 3 are literally sitting there completely empty? Boom, you hit a stack overflow the second stack 1 crosses its 1/3 line. Your entire program crashes, and you still have 66% of your array just sitting there collecting dust. It is a total waste of precious memory.
So how do we fix that? Enter approach 2, the flexible ends and middle strategy. We're pivoting to a clever little hacker trick you'll see heavily debated on forums like Stack Overflow. If fixed division is too rigid, let's make it dynamic. Here's the play. You pin stack 1 to the far left at index 0, growing right. You pin stack 2 to the far right at the end of the array, growing left. And then you drop stack 3 dead in the center and force it to grow outward in an alternating left-right pattern into the empty space. As you can see, this creates a much more forgiving, shared memory arena. The empty gaps aren't walled off anymore. Stack 1 and stack 3 can share that left side gap, and stack 3 and stack 2 can share the right side gap. Nobody is boxed into just a third of the array anymore. Now, does this delay a Stack Overflow? For sure. But honestly, it creates an absolute nightmare for you, the programmer. If stack 1 suddenly bumps into stack 3, you have to literally shift the entire middle stack over to the right just to make a tiny bit of room. And the second you start shifting elements around, say goodbye to our constant time requirement. It turns into highly bug-prone, inhomogeneous code that no one wants to maintain. Which finally brings us to approach 3, the simulated linked list. If you really want to show off in the interview, this is the senior engineer flex. We are going to entirely abandon the idea of physical array boundaries.
Instead of fighting with where things physically sit, we treat the array as one giant shared pool. Every time you push an item, you store its value, but you also store a backward pointer that tells you exactly where the previous item for that specific stack lives. At the same time, we keep track of every empty slot using a completely separate stack called the free list.
It's all about relationships now, rather than rigid locations. Need to push an element to stack 1? You just ask the free list. Hey, got an empty slot? It hands you a random empty index. You drop your data in, point it back to the old top of stack 1, and update your top pointer. Pushing takes a slot off the free list. Popping gives it right back. No shifting required, and it all runs beautifully in constant time.
The absolute beauty here is that wasted space drops to literally 0. One single stack can eat up the entire array if the other two are empty, and it won't crash until the array is 100% full. But always point out the trade-off to your interviewer. You are paying a pointer tax. You have to sacrifice a bit of memory overhead to store all those extra backward pointers next to your actual data.
All right, trade-offs and takeaways. We've just walked through 3 entirely different mindsets for the exact same problem. How do we wrap this explainer up and leave them totally blown away?
You look at the whiteboard and you just leave them pondering this. How does our logic scale if we suddenly need, say, n stacks in a single array? Well, that simulated linked list approach we just nailed, it scales perfectly to n stacks, precisely because it relies on pointers instead of physical walls.
Actually, fun fact, scaling this up dives into some seriously heavy computer science theory. Researchers like Michael Friedman and Deborah Goldsmith have written entire papers pushing the absolute physical limits of space and time complexity here. They've designed theoretical data structures that use directory blocks to hit mind-bending limits, like an O of square root of n space complexity when managing multiple stacks. Pretty wild, right? At the end of the day, this whole explainer boils down to one undeniable truth. Great engineering isn't about finding a single magic bullet. It's about mastering trade-offs. Do you take the simplicity of fixed division, or are you willing to pay the memory tax of a simulated linked list to guarantee maximum space efficiency? So I'll leave you with this. With all your chips on the table, which approach are you pushing to production?